Finally, I'd like to talk about how we can use some of these trig identities in problems that are similar to the homework. So, example 1. Suppose I wanted to figure out the cosine of 5 pi over 12. Well, 5 pi over 12 is not a common angle. Okay, so how can I write it in terms of common angles whose values I do know? And it just comes down to, can I write 5 pi over 12 in terms of angles I do know? Well, 5 pi over 12 is 2 pi over 12, add 3 pi over 12, yes? But 2 pi over 12 is pi over 6. Hey, that's a common angle. 3 pi over 12 is pi over 4. Hey, that's another common angle. The point being, cosine of 5 pi over 12 is the same as the cosine of pi over 6, add pi over 4. Well, now I can use the what? Angle addition formula for the cosine, right? Which was D. Now if you go up here to D, angle addition for the cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. So I just plug things in. Cosine pi over 6, cosine pi over 4, minus sine pi over 6, sine pi over 4. Now, these should be values you're associated with. Cosine pi over 6, root 3 over 2. Cosine of pi over 4, root 2 over 2. Sine of pi over 6 is a half. Sine of pi over 4 is root 2 over 2. If you clean things up, this is root 3 times root 2 all over 4. That's root 6 over 4. And this is 1 times root 2, so I get root 2 upstairs, 4 downstairs. Bottom line is square root of 6 minus the square root of 2 all over 4. How about that? Another example. Suppose I wanted to figure out the sine of, and this is 7 pi over 12. Well, again, I just need to be clever enough to write 7 pi over 12 as a sum or difference of common angles. Well, 7 pi is 3 pi add 4 pi, and 3 pi over 12 is pi over 4, and 4 pi over 12 is pi over 3. So 7 pi over 12 is pi over 4 add pi over 3. Well, both of those are common angles. So now I can use the angle addition formula for the sine. That was G. If you go up to G, sine of alpha plus beta is sine alpha cosine beta add cosine alpha sine beta. So here we go. Sine pi over 4 cosine pi over 3 plus cosine pi over 4 sine pi over 3. Sine pi over 4 is root 2 over 2. Cosine of pi over 3 is a half. Cosine of pi over 4 is root 2 over 2. Sine pi over 3, remember pi over 3 is 60 degrees, is square root of 3 over 2. Clean things up, root 2 add root 6, all divided by 4. All right, so that's the way you handle these kinds of problems, which you'll come across in the very first part of the homework. All right, the second part of the homework, I give you some trig thing, and I say write in terms of sine or cosine only, or perhaps I say simplify. So this is secant of x minus pi. Well, secant can be written in terms of cosine. In particular, what? Secant's 1 over cosine? So the secant of x minus pi is 1 over the cosine of x minus pi. But now this requires the angle subtraction for the cosine. And what's the angle subtraction for the cosine? Well, I see I've made a little error here. It is cosine x, cosine pi, what? Add sine x, sine pi. Okay, but what's the cosine of pi? The answer is -1. Figure out where on the unit circle you are. What's the sine of pi? The answer is 0. So I get -1 times cosine x downstairs, and I get secant of x minus pi is -1 over cosine of x. Again, the angle subtraction formula for the cosine is found up here near the top. Cosine of alpha minus beta is cosine alpha cosine beta. Add sine alpha sine beta. Notice the cosine is weird in that it's minus here and plus there, whereas the sine, it's plus here and plus here. I like to say the sine is right on the sine. Get it? All right, finally, example 4 is how do we prove a trig identity using these trig identities we already know. So here's one, tangent 2x. Show that it's equal to 2 tangent x over 1 minus tangent squared. Well, here's what I have to say about trig identities. If you prove a trig identity, technically you need to start with one side and get it equal to the other side. It's not kosher to move things from one side to the other. It's not kosher to multiply both sides of an equation by something. You start with one side and you get it equal to the other side. And so let's think about proving this. These are not meant to be hard, but meant to give you some practice. So I usually start on what I call the scuzzy side, the ugly side, because my mind works, I simplify better than I mess up. All right, so let's start on this side. 2 tangent x over 1 minus tangent squared, okay? Let's write everything in terms of sines and cosines. That's 2 sine x divided by cosine x upstairs, and 1 minus sine squared x divided by cosine squared x downstairs. Now, if I want to clear fractions, this is a compound fraction, I need to get rid of these things. What can I multiply top and bottom by, some special 1, that clears fractions? The answer is cosine squared x. So that's what I'm going to do, multiply top and bottom by cosine squared x. All I've done is really multiply by a smart 1. But when I do that, cosine squared times this, my cosines cancel and I get 2 sine x cosine x. Downstairs, cosine squared x times this, I've got to multiply it by each one. What do I get? Cosine squared x in the first, and then my cosine squareds cancel, so I get minus sine squared. Now I'm there, and I look up at the top and I think, 2 sine x cosine x. What's that? And the answer is 2 sine alpha cosine alpha is sine of 2 alpha. And by the way, cosine squared alpha minus sine squared alpha is cosine of 2 alpha. Those are circles I and J. Go back down here. By I, 2 sine x cosine x is sine of 2x. And by J, cosine squared x minus sine squared x is cosine of 2x. All right? But sine 2x over cosine of 2x is exactly what? Tangent of 2x. And there you have it. I started with this side and I ended with that. And that's the way you handle trig identities. All right, those are the only examples I want to look at. Similar to the homework problems, you should be in relatively good shape for the homework in Chapter 4.